Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College in the UK, and this is a new episode of the podcast Turbulence at the Exascale. If you're not familiar with the podcast, we are trying to gather the view from the scientific community regarding the challenges and opportunity associated with exascale computing to study turbulent flows. And this podcast is part of the UK initiative called ExCALIBUR, which is an initiative over 5 years led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And the idea is to develop new software algorithm to harness the power of exascale computing. And this podcast is also linked to the UK Turbulence Consortium. So I'm very pleased to say that today we have an international guest from Italy. So our guest today is Professor Sergio Pirozzoli from Sapienza University of Rome in Italy. And I'm pretty sure you know Sergio. He has a lot of research activity in high performance computing, CFD, of course, high speed flows, direct and large simulation, and so on and so on. So it's going to be very nice to have a chat with him today. So good morning, Sergio.
Morning to you.
For those who don't know you very well, maybe please can you tell us a little bit more about yourself, where you're from, what you have studied, and how did you end up at the Sapienza University of Rome?
Well, to be honest, this is not a very adventurous story. As well, in Italy, typically we say you die the place you are born. And actually, this is my case. I was born in southern Italy, and then I did all my studies at Sapienza University. I took a degree in aeronautical engineering. That was my master's degree. Then I spent some time. Then I got my PhD also from the same university. So I did all my studies there. Then I had some short-term visits at Caltech, which was quite fun, working with the team Colonius there. And after that, I basically went back to my same university as I was lucky enough to get a permanent position in a reasonable time. So this is it. Well, that's a very short story.
No problem. And may I ask you, how did you become interested in computational fluid dynamics and in turbulent flows? I mean, you said you did your undergraduate in aerospace, aero engineering, but how did you say, oh, turbulent flows is my thing?
Well, this was not the very starting point, to be honest, as back in my master thesis times, we were studying hypersonics, laminar flow. And together with my advisor, Francesco Grasso, we realized that, I mean, at those times, there was some growing interest about high performance computing, but those were very early days. I'm talking about 1997. So I remember my advisor was far-sighted enough to say, okay, let's try this. And we decided to set up a parallel code, which was not something very common at those days. And I remember we were able to run on like 128 cores on a T3 machine, which was the best machine we had at that time. And that was really fascinating to me. And I mean, that really started my interest in HPC, writing efficient codes and making these codes to run on big machines as fast as I can. That was really my starting, the reason that my interest began.
Great, thank you. And so you said you're spending all your career pretty much at Sapienza University. And so may I ask, what's the best thing about working at Sapienza?
Well, I would say at least three things. One thing is the city. I don't know if you visited it ever, but I mean, Rome is really beautiful. And my office is very nicely located. I mean, if you should come and visit us sometime.
Absolutely.
It's really in very downtown Rome, and it's a few steps away from a Colosseum. That's very nice location. Weather is gorgeous. So and these are the best things I would say. But to be more serious on the scientific side, I think in Italy in general, we have a lot of freedom. I mean, there's no big pressure on us professors. I mean, you don't have to be super productive. I mean, of course, we have some control, but I mean, we are not really pushed so much. The other good thing, although it seems paradoxical, I mean, research funding, especially basic research funding, is so little in Italy that you don't have to spend all your time writing proposals, as maybe some of my colleagues are doing overseas. So this is good because it saves a lot of time to do basic research. So I think this may be an advantage in some sense.
Great, thank you very much. Before we start, I have a personal question. I used to interact quite some time ago with Paolo Orlandi, and I wanted to ask you, I know he's very old and I know he's retired, but I can see that you are still publishing with him. So I was wondering how Paolo is doing.
Well, he's doing great. In fact, as you're saying, he retired a few years ago. So he's no longer a young person, but still is extremely productive. I mean, for those who don't know him, he's basically the one who brought, the study of turbulence with computers in Italy. Yeah. After spending a lot of time in Stanford. He used to be my office mate, and this is one of the reasons I'm working so much with him. Currently, he's, well, just to tell you, the kind of guy is working together with me, is basically modifying our pipe code in order to put roughness in the code. So that's going to be our next study.
So he's still doing some coding. That's amazing.
Sure. That's he loves it. Well, he does at least three things. He does coding. He does mountaineering and skiing. That's what he does.
Wow, that's great to hear.
Thank you. Great. Sure.
Great. Right. Let's talk about. Can you introduce us to what research are you doing these days? What flow are you studying and things like this?
Yeah. Okay. My general interest over the years has been mainly focused in the study of wall turbulence. So we basically study wall-bounded flows both in the subsonic, incompressible regime and in the compressible regime, I would say. So this is my main field of research. Many of my recent publications have been dealing with the study of fundamental DNS studies of flows over solid boundaries like channels, boundary layers, and pipes recently. But I have many other fields of research. Hypersonics is certainly a field that I'm currently interested in. I'm receiving some funding from US Air Force to do that. And so we are studying, for instance, three-dimensional effects in shock boundary layer interactions in the turbulent regime. But I have other side projects, which are maybe not really side projects. We are working on roughness. We are starting to work on roughness nowadays. I think this is challenging because computationally speaking, at the moment, there's been no single DNS of a real roughness, meaning small elements and high enough Reynolds number that you can have some scale separation. So this is what we are working on right now. Other things I'm also interested in is conjugating transfer in cooling channels. This is more, a typical application of rockets. This is relevant. So, for instance, we are studying ducts, rough ducts, with conjugate heat transfer, and see if, for instance, you can get any gain, any benefit from some artificial imposed roughness. We also have projects in multi-phase flows. For instance, one of my former students is working on wave breaking, which is an exciting subject. And recently, we have also done some publication with Alfredo Soldati in Vienna. We have done some very nice publication, I would say, about turbulent convection. Well, convection in porous media. I would not say turbulent, but this is really fascinating subject. But these are my main fields of activity right now.
Great. Sorry, I'm a bit curious. You say you're going to start looking at roughness in wall-bounded flow, and just once again, it's my own curiosity. When you are talking about roughness, do you have any idea of what roughness size you are going to be dealing with in terms of, so if we take the boundary layer thickness, are you talking about something that is going to be 10 times, 50 times, 100
No, it's
times
going
smaller?
to be it's going to be more than 50 times, which is basically the rule of thumb, to call it roughness, according at least to Jimenez's review a few years ago. So that's going to be more in the order of 100.
100. Okay, so it's going to be challenging from well to model this, right?
Yeah.
Good. Thank you very much. So not only you are studying wall-bounded flows and high-speed flows, you are also doing some software development. And I wanted you to talk a little bit more about streams and the hypersonic task-based research solver that you have been working on in the last few years. So can you tell us a little bit more about what numerics you are using to do your research?
Yeah, well, over the years, I have been working a lot on computational model development. So I have basically written all the basic algorithms for compressible flow from basically scratch. So I think I have given some contribution to the field, and eventually, after 20 years, we realized that I think we have found an optimal arrangement for compressible solvers, which includes the use of energy preserving discretization, central discretizations for smooth parts of the flow, and the limited use of shock capturing schemes only to where they are strictly needed, like cross shock waves. Mm-hmm. So we have this hybrid algorithm that we have developed over the years, and which is basically the cornerstone of the Streams code. Streams is a GPU implementation, actually, of our now traditional local solver, which has been mainly developed by Matteo Bernardini. Matteo is very clever guy. He used to be my student, and now is my colleague in Sapienza University. And he carries on the development of this solver, which is very well written, and it's extremely fast to run on GPU machines. It has a number of features, like, for instance, it is also having the capability to handle complex geometries through the immersed boundary technique and many, many other features. So you can refer to him if you need additional details, but this is going to be, I think, a code. This is open source, so I hope many people in the community are going to use it.
And sorry to interrupt you. You said it's GPU. It's written for GPU. So is it written
GPU? I'm sorry.
Yeah, is it written in CUDA or OpenACC?
That's a CUDA.
It's a CUDA. Okay.
Sure. The other code, which is called HTR, that was a code developed by Mario Di Rienzo. I'm not directly involved in the code. I mean, he just asked me the favor to give him some suggestions on how to change the code, the basic discretization, which we did, and it was quite successful. But well, I'm not taking any,
I will. I've invited Mario Di Rienzo, so
Mario is also a really, really clever guy. And this code is more oriented, I would say, to combustion, high-speed flows, reacting flows. He has this kind of capabilities, and I think this is also very interesting as it exploits. I don't know if you're familiar with the Legion. You know what it is? Well,
yes, I've heard about it. I've seen a presentation from the US, from Sandia, that they were based there.
Yeah, that's basically a joint, effort between Stanford and Sandia. It is basically a programming system which basically adapts to the machine that you run on. That's to me is very interesting undertaking, as it basically allows you to write your code. Of course, you have to use their own programming language, which is Regent code. But once you have written your code in that language, you basically can run on any machine in principle. And also these environment will allow you to do like load balancing, and data distribution across tasks almost automatically, and also to exploit all the features of your architecture. Like if you have a heterogeneous architecture with CPUs and GPUs, it will exploit it. So that's to me is quite promising.
Excellent. So now I have a little bit more a specific question. So you say you have developed some hybrid algorithm for high-speed flow with shocks, and if there are going to be any particular issues with those algorithms if we are looking at the parallelization strategy, or do you think they are going to be able to scale very well on for larger and larger computers?
Okay, this is a simple question. As I mean, we never had any problem with implementation of these compressible flow algorithms on parallel computers. The main reason is that compressible solvers are typically fully explicit.
Of course.
Since you don't have a Poisson solver, I mean, if you march in time, then you're fully explicit, and communications only occur across boundaries. Which makes, of course, the data exchange not massive. This is why, for instance, Matteo's code is running with incredible scalability performance. I mean, you don't lose much in communication. So I don't think this is going to be an issue also on the next generation machines.
Excellent, great. I have one other specific questions before we talk about exascale computing. Is I've seen your recent work called Reynolds number trends in turbulent pipe flows, DNS perspective. So can you tell us a little bit more about this paper?
Well, this is something I'm really proud of. This is actually the result of concurrent efforts with Roberto Verzicco at Tor Vergata University, who is a very well-known fluid dynamicist. And we have had some contribution from NVIDIA Corporation, Massimiliano Fatica and Josh Romero. They were taking care of GPU porting of the pipe code, which was really unbelievable. And so, I mean, we were able to get, well, pipe flow in general in the wall turbulence community is not very much, populated from the DNS side, mainly because you have some additional computational issues like, axis of symmetry, which you don't have in channel flows. So you have singularity there if you use cylindrical coordinates. So these kind of issues are not easy to tackle. And but I think this is a fun, well, for obvious reason, it is a fundamental flaw. Most experimental studies have looked at pipe flow, and we were able to reach with this code on the Marconi 100 machine. We were able to reach RE tau friction Reynolds number like 6,000, which is quite high.
Yeah.
I mean, for DNS, and we found some interesting results. I think the first thing is, I mean, von Karman constant, which is supposed to be different in different wall bundle flows. It seems to be, to me, pretty much the same. It's around 0.39, very little difference with other flows. And we also find some interesting results regarding the behavior of quantities that people from the wall turbulence community look at, like, the peak velocity variance in the buffer layer, which, well, that would be a lot to discuss, but we have been able to confirm some theoretical findings and maybe refute some other.
Great. Well, if you are interested, then you should have a look at this paper for those who are listening to this podcast. Great. Final question. Well, let's start talking about high performance computing. So you organized, or you were part of the organization back in 2018 of an advanced course on high performance computing of big data for turbulence and combustion. And there is now a book that is available. So can you tell us a little bit more about this school or this course and the book? The following.
Yeah, well, the first thing I should say that the school was given at CHISM. I don't know if you heard about it, but it's
yes.
Yeah, it's a very active center. It's
Yeah.
actually International Center for Mechanical Sciences, which is based in Udine. And the director is currently Alfredo Soldati, I was referring to earlier on. Well, this particular course we organized with Tapan Sengupta. And I think this was a nice attempt to put together, people working in the development of DNS database, also looking at the algorithmic part of it. So there was some discussion about the fundamentals of numerical discretization, and then, well, the idea was, to see what to do with the data that are generated with large DNS databases. So we had the experts with some special expertise in the development of reduced order models, for instance, from big DNS data set. And we also had the lectures from Gianluca Iaccarino, who is, for instance, using DNS information in order to synthesize advanced turbulence models, so modifications of existing turbulence models based on DNS knowledge. And I think that was a very nice course, and well, I think the book is also quite interesting.
I agree. I came across the book, and it's a very interesting compilation of contribution. Great. Right. Let's talk a little bit about exascale. So if tomorrow I give you access to an exascale computer, and let's say you are able to use it at full scale, what will you be able to study that you currently cannot study? Or what will you do with it?
Yeah, the most obvious the most obvious answer is that since I'm working on a pipe, I would like to run more of a pipe, like pushing Reynolds number yet higher. Well, there is some fundamental interest in doing that. Well, first, there is a computational interest. For instance, if you project, the Reynolds numbers which have been achieved in wall-bounded flows in previous days, I was imagining that we should reach RE-tau like 10,000 in the early 2020s, and we are almost there. So yeah. The first motivation is reaching that limit. But I mean, to be more serious on from a fundamental scientific standpoint, there are issues which are open. For instance, we know that there are clear violations of strict wall scaling, as for instance, the peak velocity variance I was referring to is increasing logarithmically with the Reynolds number. But there are some theoretical suggestions that this trend should stop at some point. Experimental data are not helping much, as they cannot resolve with good accuracy the buffer layer. So DNS would be, I think, invaluable in order to eventually sort out this issue, which is very important because this tells us something about the fundamentals of wall turbulence, whether wall scaling should, be restored eventually at high enough Reynolds number or not. This is, to me, quite an important subject.
Right, and you have a good understanding of the CFD landscape in Italy, and I was wondering, do you think the CFD community in Italy is ready for the transition to exascale computing, or do you think there's still a lot of work before being able to use supercomputers?
Well, we are still in the middle of a migration towards GPU-based architectures. So many of us, if not all of us, have started the migration to new GPU-based solvers. So in order to tell whether we are ready or not for the next step, it would be good to know what kind of computer architectures we should expect. Of course, at the moment, I don't think anyone knows. Mm-hmm. But I think in this respect, we should. What I hope for is some support from computing centers, and for instance, from the BRACE European initiative in this respect. Porting codes in these troubled times would be, well, in this times where some change, we don't know what, but some change will occur. Some support from computer scientists will be certainly very important. This is not something we can do on ourselves with our own efforts, I think.
I agree with you. Now, it's a rather strange question, but I always like asking this question. So if there is one thing you could change in high performance computing, and I'm talking about hardware mainly, what would you change? I mean, are you happy with how supercomputers are designed these days, or would you change anything?
Oh, well, I think I see two bottlenecks right now. One bottleneck is related to GPU-based machines. As you may know, GPUs have limited resident memory, and this is, I think, at the moment the main bottleneck we find. And for instance, we can run much bigger computations. I mean, because computing power is not a big issue. It's not. Now the main bottleneck is memory. So we are back to being bounded by memory issues. Because as soon as you get out of the GPU memory, then your code will go much slower than if you stay in the. So I think this is one hardware bottleneck. I see that there are some new graphic cards which are coming out, which are maybe overcoming this issue, but at the moment this is one issue, and the other issue is the storage, because I mean, at least this is one problem I find, is that we never know where to put all this data, and also supercomputing centers will provide you with computer hours easily, but they are much more stringent on the storage. So I think this is also an issue. Somehow we have to find a way to store all this information, possibly for the mid to long term.
I agree with that. Hopefully solutions will be found very soon. Right. My last question is, so there's a lot of talk about exascale computing, and I was wondering if you think that we are going to have, after the exascale computers, if we are going to have a revolution with brand new hardware, or do you think we are going to still have like more GPUs with more core, more memories, more energy efficient? Well, so how do you see HPC headed in the future?
Well, I don't know. I don't have a crystal ball. Well, if I had a crystal ball, then I would be very curious to see the answer. But the way I see it is, I mean, we really don't know. But the reason is that the future of HPC is not so very much related to what we are asking to HPC centers, because developments in computer architectures are mainly coming from common users. For instance, GPUs have come out because there was some demand from the general public. So we don't really know what's going to happen in the future, at least for this reason. And well, one thing which might be a game changer is quantum computing. This is something that people are talking about, but as far as I know, well, this is not very much suitable for scientific computing, at least at the moment. But clearly, well, that can be, there is a chance that maybe at some point there is some change in the paradigm which will make it also available for us. At the moment, this is very futuristic. I tend to see that in the midterm there's going to be evolution of current architectures which are based on mix of CPUs and GPUs, hopefully with some improvement.
Great. Well, thank you very much, Sergio, for your time and for your inputs. And it was really nice talking to you. And we wish you all the best for your future research and your work on roughness with Paolo in particular. So thank you. Thank you everyone for listening to this podcast. As usual, it will be made available on YouTube and SoundCloud, and the links will be put on Twitter, and you can find all the information on the UK Turbulence Consortium website. Just Google UK Turbulence in one word and you will find everything you need. So thank you very much for listening to this podcast, and hope to see you soon in a new episode.